put in the last piece we need on this simple beam type problems we've been doing. We've been looking at all kinds of things. And some, you'll recognize this one as an over constrained beam. There's more supports there than we could solve for, except we'll be able to do this for the last time. Remember, every time we wanted to do a statically indeterminate beam, which this is because of there's too many supports for the number of equations we have. Every time we wanted to do some kind of statically indeterminate beam, we needed something about the deflections. So we're getting our last piece of the beam deflections today as we then put all this together, and we'll be able to do statically indeterminate beams with tomorrow. What we're working on today is the actual deflection of these beams. A beam loaded like this, and I just made up some type of picture. We know that it won't go up, down any because of the load at the supports, but it's going to bend in between. Bend something like this here, and then well, it wouldn't do that, would it? Whatever. You can kind of come up with a basic idea of what it's going to do, and that's always a good idea. Look at the loading, look at the constraints on it, which for the most part are these supports, and see if you can get sort of an eyeball picture of what the beam would look like if greatly exaggerated in its bending. What we're going to do today is actually come up with the equation for the curve of the beam when loaded. It's known as the elastic curve because all the materials in this class are considered elastic. They bend predictably. They, for the most part, in the design considerations we make, they return to their original state when unloaded. What we're going to do is come up with the actual equation, and we'll call the deflection V. That's going to be that's the horizontal, the vertical position of the beam from some neutral position that we start with. We're going to come up with the equation for that beam as a function of position along the beam. That's our goal for today. So, as usual, x is down the length of the beam. We want to find out precisely what the mathematical curve is that will give us the shape of the beam once loaded. And of course it's going to depend upon the loading, it's going to depend upon the constraints, where it's supported, how it's supported. The pin supports are very different than the cantilever type supports that we see. But we'll put all of that together as we need to through today. So that by the end of today, we'll have this equation, the actual mathematical function for the curve a beam makes when loaded, for some fairly simple ones, and then we'll do some more complex ones tomorrow. So that's the basic setup of what we want to do. I'm going to number these equations as we go through. What we're going to do is we're going to start here and sort of build backwards until we hit something that we've done before. And then once we hit that something we've done before, that's where we can start the problem, and we build back to here, and we'll have the curve after a few basic, fundamental Calculus 1 steps of integration as we go through this. So that's equation number 1 as we start going through these. That's our goal. So we're going to build back through a couple, hit those, and then we're going to come back in some problems and actually get to this curve when we get there. All right, so zooming in on some little part of this beam here in some kind of loading and bending situation, we'll have some position X and some amount of deflection of the beam. So we'll have a little piece of the beam we've zoomed in on. Looks something like that. Whatever loading it was, it made it deflect wherever it's going to go. It's just a generic conversation with this here. We've got, of course, the neutral axis passing down the beam somewhere, depending upon what the shape of that cross-section is. If the neutral axis is up at the top, then it's a beam that's a bit wider at the top and cross-section than usual. That's not important yet. That just gives us a place from which to measure things. And so the parameters of interest right now are things like the curvature of that beam, which is the local radius of that curvature at that point. And it changes all the way along the beam. It itself is a function of x, because it's in one direction here, and then it's down here somewhere, and it changes all the way along the beam. In fact, there will be places where, because of the loading and the constraints, that the beam actually has no curvature. It may have some slope, but it doesn't have any curvature. So the curvature is actually infinite at those places. And start bringing back in your calculus as you start thinking of the functions you looked at. The second derivative especially told you what the curvature was and how to define where you went from one type of curvature to another. What happened? All those type of spots are going to be of some concern to us today. So we've got the curvature there. At that same spot, we've got some slope to the curve of that place, and we'll call that theta. So we're bringing together then this deflection from the neutral axis, V, and we're trying to find out the equation for that as we go along the beam. You can see that fairly obviously the curvature and the slope also change with x as we go along, and all of these things are going to be related. So we know that, let's see, for that particular point, the slope of the curve, dv dx, is tan theta. So you can see we've already made one step from our curve with the first derivative. So we're going to go down a couple derivatives and then come back with a couple integrations, and we'll hit our curve, our elastic curve by that point. For very small thetas, for very small angles, which these are, because we're talking about beams that don't deflect very much. This is grossly exaggerated just so we can see it. These deflections are going to be on the order of hundredths of an inch for steel beams in typical lengths and loadings and weights and the like. We're not talking about very much. So these angles are also going to be very small. So for very small angles, it's a perfect approximation for our purposes that the angle will be very, very close to the tangent of the same angle. If, of course, our angle measurement is radians. And you can set your calculator to radians, put in a really small number, take the tangent of that, and you'll get the really small number virtually unchanged. You have to go out to several decimal places. So this is, for the most part then, well, let's put it together then. Here's our second equation. If we can find something about the slope, we can integrate this, and we'll be back at our curve, our elastic curve. So this is the kind of thing we're doing as we march through this. So our next step, I have to bring out something. I'm sure most of you could recite this verbatim, as you can with most of your obscure Calculus 1 facts. No, nobody knows how to finish that on the fly? Yeah, me neither. That's not what we're here for. The curvature of an elastic curve, you will remember something about when you see it, has to do with the second derivative of the curve we're talking about. And by curvature, you remember the convex up, convex down type of things you were looking at when you looked at the second derivative in Calc 1. We'll also have on the bottom then 1 plus the slope squared to the 3/2. Oh, you're all nodding now. Now that you see it, you go, yeah, okay, yeah. Now I see. Yeah, it's a little early, so I just yeah. Travis, take one more sip of coffee, and I would have been right there with you. So that if you went back to your calc book, you'd find that in there. It's something you went through one day. The thing that that we need is the fact that this, as we've already established, is very small. So if we square something that's very small, it's even very smaller. So this will tend to 0, and then that just makes the denominator 1, and so the curvature is essentially equal to the second derivative of the elastic curve. Now, that's not yet equation 3. We're not quite there, but we're getting close. We've now got something about the curvature, we've got something about the slope, we've got something about the actual deflection of the beam itself. So, hang on to this little bit here, because we'll need it in a second as I establish a little bit more stuff. We'll be pulling that back in just a split second. So the part we need to put together now is very similar. I think we've done exactly this, in fact, when we did look at curvature some time ago. Again, a little piece of the beam in greatly magnified and greatly exaggerated curve, where we have this neutral axis here. We have the curvature down to the neutral axis is something we've just got a hint at over there. We're going to pull that back in a little bit. And we need, let's see, and then depending on which way we're going, don't forget that from the neutral axis to the extreme part of the beam, we always call that C. But anything else in between, we called Y. So let's just go up to some arbitrary point, Y. And in fact, for our measurements, that's actually in the negative direction. So the curvature down to that point is rho minus Y. This should look a little bit familiar. I think we did something like this about 7 or 8 weeks ago or something. This very same drawing. So this piece of the beam that we've got cut out here is delta x long. But now that the beam is loaded, has deflected, and is under strain, the length of a piece, oh, let me get the pieces marked right, yeah. When the beam's unloaded and this is straight, then the neutral axis distance is equal to the line at Y, but now that's strain, and so we'll call that delta x prime. And then we can look at the strain in the x direction as delta x prime, the strained length at some height y, minus delta x over delta x. And then we can set these up as arc lengths. So the arc length of delta x prime, by the way, we have an angle here of delta theta. So the arc length of that delta x prime is rho minus y delta theta. That's the delta x prime. Delta x is rho delta theta, so we subtract that off, rho delta theta, and so this is over rho delta theta, and of course the delta theta cancels. And we can then simplify this a little bit. We've got rho minus rho, so that leaves just the minus y. We get minus y over rho as the strain at any place away from the neutral axis across the beam. We did that a couple weeks ago, I think, when we were setting up the bending. So that's a familiar little piece there. All right, we can relate that strain to the normal stress with Hooke's law. Remember Hooke's law, the Young's modulus is the stress over the strain. And we've now got that strain, so this is minus E y over rho. But we also know that this normal stress is minus m y over I. The bending is caused by the load. All right, right there is the 1 over rho that we just developed as the second derivative of this curve that we seek. Our ultimate goal for today is that actual curve, and we've now just tied the second derivative of that curve to the normal stress. All right, so let me rearrange things a little bit. So m, the moment, which remember is itself a function of x, changes down the beam. In fact, maybe we'll put that in just to remind us. The moment as we go down the beam is now, the minus signs cancel. We have E times I time, and the y's cancel, times the second derivative. And that then is equation number 3 of the ones we think. Now, we know very well, since we even started this back last fall in statics, we know how to find the moment as a function of x. So if we can find the moment as a function of x, we can integrate it twice, and we'll have our curve. But just to be a little bit more complete, let's remember a couple other pieces that we need. Well, we might need. It just depends upon where we are in the problem. We also know that the shear as a function of x is the first derivative of the moment. We use that putting together our shear moment diagrams. But we know now that the moment itself is EI, so this becomes the third derivative of the elastic curve we seek. So we might have a problem where it's just a lot easier to find the shear as a function of x than the moment as a function of x. And so we start integrating from there, and we integrate back to our curve. And that's exactly what we're going to do today. And then the last little piece is that we can relate the shear to the load. And if you remember, there's a minus sign in there because a downward load we consider to be a positive load because that's what most loads are. And then that, of course, is this quantity EI. And remember, that is completely load independent, that E times I. E is a function of the material of the beam itself, whatever material was chosen for the beam, and I is a function of the geometry of the cross-section. So those two things are completely load independent, which is why we typically pull them out. And then we get our fifth equation now as this fourth derivative of our load curve will be the load itself. Works particularly well if we have a distributed load. If we have a uniformly distributed load, then it might be easy to start right here and start integrating backwards. All right, so what I want to do is squeeze in here are all our curves. So we have the load curve we seek in the end. There's not much to it, but I gave it a rating of our first equation, and then we had the first derivative of that is the slope. But since these angles are so very small, that'll be the angle itself, because the tangent equals the slope. And so there we are. It's all set up. Everything's ready for us. Except for the mechanics of actually doing it, because you know that as we integrate back, we get constants of integration. Those constants of integration are solved for by using the boundary conditions on some of these loadings. For example, any place we have a simple pin support or a roller support, then the beam, whatever it does due to the loading, it will have no deflection at that point. So that'll be a boundary condition, wherever that happens to be. Maybe at the end, but maybe in the middle of the beam. Depends upon where that support is. At this x, V equals 0. For example, on a cantilever beam, not only will V equal 0, there won't be any deflection here. No matter how you load the beam's not going to drop down at the support any. But it's also true that the slope will be 0 right at the wall there. That's what cantilever supports do. That's one of the things, one of the purposes of them is that there'll actually not be any slope at that point. And we'll bring in other boundary conditions as we need. Those are just probably the two big ones. In table 12.1 in your book are the other typical boundary conditions that we're going to need to solve these problems. As we go through these integrations, depending on how many we have to do, every time we integrate, we get one constant of integration. For every constant of integration, we need at least one boundary condition to solve for that constant of integration, and we'll be able to then find the whole problem. All right, so let's work through one of the simplest examples we can. And this one's right in your book, so there's no worry about writing this down. Just pay attention to it as we go through it and imagine what's going on with it. So, simple cantilever beam with one single point load at the end. And again, this is right out of the book, so relax, put your pencils down, take your coffee up, sit back a little bit, put your feet up, because I'm going to do all the work here. Got your book 12.1? Would you like me to put it up on the projector real quick to show these? It's really nothing more than these pictures here. Go back a little bit to table 12.1. There it is. There's table 2. See, it's just the different types of supports and constraints. I just put up two of the most common ones that we'll use, but we'll do all of them as we go. So beam of length L, and we'll measure X from that free end where the load is. All right, so just to get going here, we'll do a quick free body diagram of a piece of the beam. We know that let me do it the way the book does it. Yeah. Start with everything drawn in the positive direction, and then if it gets a negative sign, we'll just keep it there. So there's our free body diagram for this simple beam. We know that V equals minus P, and M must equal Px. And we'll need a minus sign in there.
Why do
they
put them both in the same direction?
This is our convention for positive V. That way we get V equals with the negative sign, the proper negative sign, because we're going to need that. We're going to need to carry that all the way through, that minus sign, because it's going to give us the proper direction of the deflection at the end. We're going to have some loadings where the deflection will be down and some loadings where the deflection will be up, depending on how the beam is bending at certain places. And we're going to need that minus sign to carry all the way through. So there's a minus sign on there too, because the shear is actually up, turning the beam that way. We need a moment that way, so we'll have a minus sign there. So we've got the moment as a function of x, and we can start right here then. So we've got moment as a function of x is minus Px, and that equals E, I, and it's the second derivative of this curve that we seek. So we can now integrate. So we'll integrate through here. E I dv dx, which is one integration, is theta, the slope, and that is minus 1/2 Px squared. Is that right? David, you keep an eye on me. I'm integrating on the fly now.
This time around, I'm actually taking notes.
David.
It's actually this much fun.
Okay, wow. Maybe when you take this course again next year, we'll just start here. Plus a constant of integration. So is that right? That's okay? So far, all the pieces there? All right, and then we'll integrate again, and we're at our curve. So v as a function of x is ei, actually what I need in here is not theta, but I put the ei on, so I need ei theta, and so our curve is the integration of that, but I've got that ei in there, but that's just a constant of the geometry of the problem, so we'll just handle that as we go. So this is then minus 1/6 px cubed plus c1x plus c2. Is that right? I think? All the minus signs, all the little pieces I need. Yeah, I think we're okay. All right, so now we have our curve. All we need to do is figure out what the constants of integration are, so we'll solve those with some of the boundary conditions. So let's see, at x equals L, the deflection of the beam, we know it's going to curve something like that, but it's not going to deflect any at that point. So we'll know that v equals 0 at x equals L. So we'll put this in here. So v is going to be 0 at this point, so 0 equals, and then I put L in, I got minus 1/6 PL cubed plus C1L plus C2. Okay, so that, let's see, so we can't solve for any of the unknowns yet, I don't think. Oh, I guess we can. We can solve for C2. Oh yeah, we could solve for C2. Oh no. We can't yet, because that's just one equation, two unknowns. So our other boundary condition is that x equals L, theta equals 0. Oh, that's a good one. That'll give us C1 directly. So that would have been a good one to start with. So E I theta, but theta goes to 0 at x equals L. So minus 1/2 P L squared plus C1. So we know that C1 is the backwards of that, because of the minus sign, 1/2 P L squared, and so we can put that into there, and then we can solve for C2. And so C2 equals minus 1/3 PL cubed. And so now we've got the whole curve. Now we can put it together. So the curve as a function of x equals minus 1/6 EI. Actually, I think I can clean it up a little bit. Yeah. Every term will have a p in it, so I'll pull a p out as well. X cubed plus 3 L squared x plus the last little piece, Oh wait, I'm missing a minus sign. That's a minus sign. That's a minus sign. But I pulled a minus sign out. Minus 2L cubed. Let me just make sure the minus sign's all right. Nope. This back one's a plus. Okay, there we go. So you've got a value for P, a length of the beam L, a material chosen E, and a cross section I. You can predict exactly where the beam's going to deflect under this kind of load.
You always start by putting everything in the positive direction.
Yeah, because if you do that, then you've got the minus sign that carries through. Because this tells us, when we put in all these values, you'll get a negative number for this, which means that the deflection is that far below the neutral axis at that point.
And that works in all cases.
Yeah.
I screwed that up for
Yeah, it is. It's a tricky thing. I think when you take this again next year, we'll just do this. We'll always put things in the positive direction as a convention right from the start. Some books do, some books don't. Some problems work out easier one way than the other, but it gets messy. All right, but in the end, we've got this nice elastic curve, and if we need to figure out what the slope is, what the angle happens to be, if we need to store a bunch of bowling balls on this, we want to see if they're going to roll off, we can figure out exactly what that is at any point. And of course it's going to be a maximum there at the end, just as you'd expect. Pretty straightforward. All we need to do is figure out the moment as a function of x, maybe the shear as a function of x, whichever one's easier, and then integrate backwards to the curve. You're going to have lots of common terms, so be careful with these. It's very easy to lose a minus sign or one of these numbers down here at the bottom. Also notice what's left over is always of the same dimension, length cubed, length cubed, length cubed, so you can use that as a check. Just one of the things you can check as you go through these. All right, that's in the book again, so let's do one that isn't, so we can work through it on our own. Alright, so again, very, very simple one just to get us started. Simply supported beam with a uniformly distributed load of magnitude W. Remember, that's pounds per foot or newtons per meter, something like that, the linear weight of the beam. Okay, we want to find the equation of the elastic curve as a function of x. And you can do this, you can put x equals 0 from any end you want. In the end, you're still going to get the same curve. All right, so let's see what we can set up to begin with here. We know this will be, by symmetry, half of the total load. The total load is omega times L. Oh, by the way, the length of the beam is L. So we know the total load's WL, and half of that will be on each reaction just because of symmetry. So we've got that reaction there. And some shear, we'll draw them in the positive direction. got this distributed load, but remember to figure out what V and M are, we'll replace that with an equivalent single load just to get the right value here. So we'll replace that distributed load with a single point load of Wx, because this little section is just we're just trying to find out the moment as a function of x, and then we can start integrating backwards. All right, so V equals WL over 2 minus WX. No, because V's got to equal that. If I add them together, if I said V, and this is in the opposite direction, it'd be minus WL over 2, and so on equals 0. So this is our way of just saying, remember, all the up things equal all the down things. And the moment must be WL over 2 times x. That's the reaction plus, no, that's the moment due to the reaction. Then we have the moment due to the load, which is in the other direction. So that's Wx squared over 2. That's the moment due to this taken about that point. So I think that should be okay. Yeah, 1/2 WLx. Yeah, 1/2 WLx minus Wx squared. Yeah, so that's okay. That all right, everybody? Okay with that one? This moment must equal the moment caused by the reaction plus the moment caused by the load, and there's no moment caused by the shear because that's right through that point. So we now know the moment as a function of x, which equals EI, second derivative, equals now this WL over 2x minus WX squared over 2. Sounds like I'm reading off a bunch of radio stations. What's next? Integrate. Now we integrate, we've got the moment as a second derivative, and so we can start integrating backwards. So E I theta, I know you're tempted to start singing EIO, that'd be fun, is now the second derivative of this. So we integrate this once, so this is 1 over 4 WLx squared minus 1 over 6 WX cubed. And remember, every one of these little pieces should have the same dimensions. So it's load, length cubed, load, length cubed. So it's got to be every place we go along. Plus a constant of integration. And then we can get to the load curve with one more integration of that equation. All we're doing is marching up the line of equations there. So this becomes a 3 when it comes down. We get 1/12 omega L x cubed. Right so far? Okay, can't lose any minus signs, can't lose any powers. So this becomes a 4. We get 1 over 24. These constants in the denominator accumulate wonderfully. You're going to have a great deal of fun tracking all those. Plus C1x plus C2. That look all right? 112, WLX cubed minus 24, WX to the fourth, yeah. Okay. We've got 2 constants of integration. We need 2 boundary conditions. What are they? What?
0 and 0.
Well, yeah, at x equals 0, there's no deflection. So our boundary conditions are at x equals 0, v equals 0. So that's 0, that's 0, that's 0, that's 0, that must be 0. So that was an easy one to put in. We need another boundary condition because we still have C1 left. Just simply at the other end, the deflection here is also 0. At x equals L, v equals 0 again. So you can put that in then and solve for C1. So that's 0. This becomes L to the fourth. So 0 equals 112. WL to the fourth minus 124 WL to the fourth plus C1L. And that should all equal 0. Is that right? Did I not, I don't think I missed anything. So good, you can solve for C1 then. And C1 is minus 1/24 WL cubed. And now we have our entire curve as a function of x. Go back to here, divide through by e over I, collect like terms. There's a w in every term, there's a bunch of l's in every term, and you can clean it up so it looks like this. W over 24 EI times minus x fourth plus 2xl cubed, no, plus 2lx cubed minus, yeah, plus 2lx cubed minus x L to the fourth. No, L cubed x. There we go. Let's see, length to the fourth, length to the fourth, length to the fourth, we're okay. So we can at least check that. We can't check the minus signs any other way than being careful, God forbid.
The second one should be 2x cubed L.
2lx cubed, yeah, I switched those. Thank you, David. 2lx cubed. That one? Yeah, we had that anyway because we pull part of it out. Okay. LX cubed minus L cubed X. Okay. And so there we now we can calculate the actual deflection. The load, uniformly distributed load, well, we can go into those beam tables we used the other day, pick a beam right out of there. Remember, one of the values given there is the linear weight of the beam, right there in that number, the beam designation. So we could figure out, unloaded just by the beam under its own weight, what its deflection will be at any point. By symmetry, we also know that the maximum deflection will be right there in the center where the slope equals 0. And so we can figure out just what that would be for various values. So you can check that. In fact, you guys take a couple minutes just to do that. Check that theta equals 0 at x equals L over 2. If it doesn't, by symmetry, we know we screwed something up, so you can use that as a check. You can also check the boundary conditions. We know what those are. And then find V max at that point. And then we'll just take the book and pick out a beam and figure out how much that deflection is for a particular beam. Travis, what's your choice? English or metric units? We'll just pick up some numbers here.
English.
All right. So steel in English units. We need E. We'll just call it 29 times 10 to the third KSI. And I'll just pick an H beam out of the table. Where that table is, Appendix B. And we'll figure out just what a Vmax is. So pick a fairly heavy beam here. Let's pick a kind of a little beam, but a heavy beam. So we'll say a W1287. Remember what these two numbers mean? What's the 12 mean? Well, actually, first, what's the W mean? Remember offhand? W means it's a wide flange beam. So it's an I-beam with what's considered a wide flange on it. So that's the W. What's the 12? 12 was the approximate height of the beam in inches.
The next one's linear.
And you get that because when you see the 12 on there, you go across and you see a whole group of those have a number of about 12 for what they call the depth D. And then the 87 is the linear weight per foot. In our problem that we just did, that's W. And so for that beam, we also need the moment of inertia. It's 740 inches to the fourth. So you can figure out real quick what the maximum deflection is at the center of the beam. Just put in L over 2 for X, the EI and W we have for that beam, and then watch your units so we can see what it looks like.
How did you choose?
Oh, and we need a length of the beam here, so we'll pick a good beam, 18 feet. In fact, I happen to have one of these beams, 18-foot beam, on top of my car right now. This one. Not here, of course, at the faculty, secret faculty parking lot. Wouldn't do it here. You guys would steal my beam.
How did you do it? No, I missed the.
I just picked them. I just grabbed your book.
X equals L over 2.
Oh, because by symmetry, we know that
Oh, yeah.
that's going to be the point of maximum deflection, that's going to be the point of zero slope. Just by symmetry, we know it. We don't always know where that's going to be, but for this particular setup, it's pretty easy to know where those would be. So I just picked a beam out of there, picked a relatively small cross section, the heaviest beam. See if we can get that thing to deflect very much. And then you can even figure out, well, what if I went out and I myself stood there? How much more would it deflect? Could I make it bounce up and down? So this will be the deflection under its very own weight. And I don't know what this number, oh, well, maybe I do. Oh yes, as a matter of fact I do. I happen to do this very thing. I thought it was brilliant doing it on the fly. So just put the numbers in so we get an idea. Now that we finally have figured out this type of deflection, we got now an 18-foot beam. That's about the width across the floor here, give or take a little bit, probably a little bit less. This room's a little wider than 18 feet, I think. But just set the beam there. Don't put any more building materials on top of it. Just the weight of its own weight will cause the beam in the center to sag by how much? And that's without any underfloor, any utilities, pipes, wires, insulation, and flooring itself, and then put a bunch of students on it. Backpacks that are too heavy, giant coffee cups, calculators. And watch your units. We have 10 to the third KSI here, we've got pounds per foot here, inches there, feet again there. So watch your units. For once. Yeah, well, take it up with the king. Huh? 4 inches, you said? No, I don't know if it'd do that even if we had a rubber beam. That's pretty far.
What's that stuff made out of? Silicone?
It'd be a little tough to build a building if you put a girder down and it sinks 4 feet.
I think we
For
could.
4 inches, you said 4 inches? Yeah, it'd be fun. You could do that, the Russian trampoline, you know what that is? That's 2 people holding an elastic beam and 1 person in the center. And they let the person bounce up and down in the middle of the beam, and then doing flips, and they come back and land right on the beam.
Cold War's over.
Didn't say it wasn't, it's just called a Russian trampoline. It's not a derogatory term, not in my mind, but I like circuses. That's why I teach. I get to associate with circus animals all day long. You can take that one, don't edit that one. We'll put that on our next ad campaign. How we doing? Anybody got any numbers? Chris? Got any numbers? David, you got something?
Yeah,
Think about other applications for this.
You what?
Think about other applications for this.
Like what?
Resonant frequency splines.
Splines, yeah. Because one of the characteristics of the elastic curve is it never has a discontinuity either in the curve itself, because that means the beam is split, nor does it have a discontinuity in the slope function, because then that would mean there would be a sharp bend somewhere in the beam, and the beam has failed at that point. These beams don't fold very well. They tend to break before they fold.
And effectively what they did during the olden days was to form beams to create a line, right?
To draw a nice curve?
Yeah.
Yeah. If naval architects
Yeah.
would take a nice flexible piece of material and they bend it, and it would just naturally take an elastic curve, and then they'd hold it down with lead weights, what are called ducks, and then they'd ink along that curve, and that way they knew they had a curve that wood itself could follow when building the hull. So that term elastic curve was no accident, and that's exactly what splines do.
I remember doing a project about splines at RIT in which used the similar methods, differentiation at multiple fixed points.
Yeah, no reason it should be any different if our beam is a 1/4-inch piece of plastic. Anybody got it yet? Chris, you got something now? 0.26 inches? What'd you get?
4.7 times 790
Some?
Feet?
Yeah, feet. That's not, I got very, just under 1/100th of an inch. Did you get that, Travis? No? Chris? I'll say yes and we'll keep going. What was that snort for? End of the term? Snort? He's thinking, I can do anything I want, he's not going to fail me now. I got too many points. We'll see. We'll see, Chris. Don't push me. Something like that. Very, very small, which is good. You can put the beam up there. You don't want a big gap that you now have to compensate for as you build other things on top of it.
Oh, that high, especially if you do something 6 inches to the foot.
Well, you had to make all the units work. This was 10 to the 3rd KSI. You probably want that in PSI. So it'll be 10 to the 6th PSI. Pounds per foot. The length in feet, you want all this stuff in inches. All right, so let's do another one that has another bit of a wrinkle to it, but it's nothing we can't handle. It just adds a couple steps, but if you're careful with your minus signs, with your constants, with your units, all that stuff, it works out. So again, simply supported beam. With a single load at 1/4. So this is L over 4, this is 3L over 4. Now, this one we have to be a little more careful with because the function for the moment is different on the left side of the load than it is on the right side of the road. And we need that function for the moment to put things together. So we'll start first with just doing the very left side of the beam. And let's see, we know that this will be 3p over 4. We just do that from statics class. I'm just doing that fast for you. That's nothing more than summing the forces and summing the moments. We can figure out what that reaction is. And so the moment as a function of x is, by the way, a little piece x long. The moment as a function of x is, we're in the right direction, is 3p over 4x. So, you guys, at least for this part of the beam, figure out what the deflection curve is. And then we've got to redo it for the right side of the beam, and then we've got to figure out how to tie them together. So, you guys do that. I'll just set up the rest of the beam. So L over 4 down to L. We do the same thing we just did there, only a little bit more. And now we've got the load in there. And you could do it from the other side, but then things get a little bit tricky of what X represents. You want X to always mean the same thing through all of these. So, start with that, integrate back twice to get the load curve, the deflection curve, the elastic curve. And let's do this. Let's call this M1, because we're going to have two of these M's, since we have two sides of the beam. So this will be M2. And just figuring out what that moment should be. Minus 1/4 px.
So the boundary condition.
Plus 1/4. Don't worry about the boundary conditions yet. Just get the curve.
That's
We don't need the boundary conditions till we've gotten all the way back to the load curve. I'm sorry, the elastic curve. So we can do the first integration, get back to the slope. Second integration, get all the way down to the elastic curve. So see what pieces you get. And then we've got to do the same thing for this one. Whatever this beam happens to be determines EI. So we're going to have two constants of integration from the left side. We're going to have two more constants of integration on the right side. We're going to need 4 boundary conditions. So let's get the integration.
over 0 to L.
Get down to VI. Actually, I'll leave it in the EI form just so you can save a little trouble. We got about 7 minutes left, so let's see how we do on this. I'll throw the rest up. Got the curve, you think? Joey, you okay? We know this now. If we integrate it once, we get the slope. If we integrate it again, we get the elastic curve itself. And luckily for the problems we do, they're all nice fat polynomials, just a bunch of little constants in there.
So here we just use the, like when X is L over 4.
No, don't do anything with the boundary conditions yet. Wait till you get them all, get both sides of the equations. Well, you can do one boundary condition, because you know that there'll be no deflection of the beam at this support. So you can take care of one of the boundary conditions. You can't apply the other side because this function doesn't go to the other side. It only goes up to the load P. Then we're going to need another function there. What we have is two elastic curves, one describing each side of the load. All right, for this one, hopefully you got something. We'll call this V1 for that side of the beam. 1/8 px cubed plus c1x plus c2. Get something like that?
C2 0.
And so we can take care of just one of them at x equals 0. The deflection is 0, so we know that C2 is 0. There's not anything else to do yet. We cannot go down to this end and apply that boundary condition because this equation does not go down to that boundary condition. So be careful about that. Yeah, Joe?
I don't know, C2 is 0.
Because at x equals 0, the deflection of the beam is 0. So that's 0 at x equals 0, so that's 0, that's 0, that has to be 0. All right, we can integrate the other one down to the deflection on the other side of the beam, which I was calling everything on that side 2. And you should get something like minus 24 px cubed plus 1/8 plx squared again length cubed, length cubed, length cubed plus c3x plus c4. Now, C4 is not polite enough to become 0 like this one did because this will be at x equals L, the deflection is 0. So, for the boundary conditions, we're going to need to solve for these 4 unknowns. One we've already taken care of. At x equals 0, V equals 0. So we've already applied that one. That's the C2 is that makes C2 0. At x equals L, V is also 0. So those are the two obvious ones, just due to the supports. Any ideas for the other two boundary conditions we need to solve for the two remaining? Actually, we still need 2. Travis, one of them.
At x equals L over 4, the graphs are equal.
At x equals L over 4, we want V1 to equal V2. If not, the beam is sheared and has failed, so we don't have any problem after that. V1 equals V2. That's just ensures that the beam itself is continuous. We wouldn't want the deflection to come down one place and then be disjointed as it finishes the curve. What's the other boundary condition?
Theta 0 there.
What?
Is theta 0 there as well?
No. It might be, but there's no guarantee. This lowest part of the beam could be right under there, but we're not sure it is. You can't assume it is, nor do we need to. There is another boundary condition that will suffice. And it is a boundary condition at that point. David?
At x equals L over 4, dv1 dx equals dv2 dx.
In other words, at that point, these two curves have to have the same slope. Otherwise, there's a sharp bend in the beam and it's not an elastic beam. So at x equals L over 4, theta 1 equals theta 2. And that's what David said. He said dV dx 1 equals dV dx 2. So there's the 4 boundary conditions. Put those into the equation. I've got the left-hand side for you. You can do the right-hand side this weekend when you're bored but you're thinking of me. V1 equals P over EI times 1/8 x cubed minus, you're going to love this, 7 over 1/28. Love these little pieces as they accumulate. L squared x. That's for the left side of the beam, V1. Then you need to do the same thing for the rest of the other side, V2. And if you differentiate this, you'll find that it doesn't equal 0 anywhere on this side of the beam, that the low spot, I believe, is on the other side of the beam. At least I think it is. I think that's the way it goes. Anyway, you can find out. Only one of these curves, and I don't have V2 for you. It was too late last night when I get this done. One of those will differentiate such that the slope is 0 on that side of the curve. One of them, it'll have the slope on the other side of the curve, which is an erroneous solution. All right. And then Monday, we'll use this to do statically indeterminate beams and some other ones that are a little bit different than some of the ones we've got here. We can do more complex ones.